Hi everyone, I came across another interesting problem today and it tripped me up when I first saw it, to be honest, and so I thought I would do a quick video about it. So the goal of this video is to find the distribution, so I'm going to abbreviate distribution, of xy when x, y are IID, standard normal. So at first glance, this looks like this would just be like a standard bivariate transformation, and it gets really hairy when you do it. But there's another trick you could do. So if you say 1/4 x plus y squared minus 1/4 x minus y squared, and we find what this is equal to, we have 1/4, and I'm just going to pull that out, x squared plus 2xy plus y squared minus x squared minus 2xy plus y squared, which gives us 1/4. And then the x squares actually cancel each other out. The y squares cancel each other out, and then 2xy minus negative 2xy ends up becoming 4xy, which gives us xy. So if we can find the density of these two guys, then we can essentially find the density of the product x and y. And that's actually a much easier problem. The normal random variables have this really cool property where the sum of any two normal random variables is itself a normal random variable. So x plus y is distributed normal with mean 0 and variance 2. Similarly, x minus y is distributed normal with mean 0 and also variance 2. Using this, we can use another well-known distribution, x plus y squared over its variance is actually a chi-square random variable. Similarly, x minus y squared over its variance is also a chi-square random variable. Why is that? Because for a normal random variable, the square of that normal random variable minus its mean over its variance ends up being a chi-square distribution. Chi-square distributions have this, so down here is the little subset, that's subscript, that is the degrees of freedom. Now the sum of two chi-square random variables is itself a chi-square random variable where you add the degrees of freedom together. So x plus y squared over 2 plus x minus y squared over 2 ends up being a chi-square random variable with 2 degrees of freedom. We can use another distribution here. A chi-square random variable with 2 degrees of freedom is the same thing as a gamma random variable with shape parameter alpha equals the degrees of freedom over 2. And we can use the rate parameter b equals 2. Now I'm doing this because it's kind of just an extra step. This is essentially our goal right here. The one problem with this right now is that we need these distributions times 1/2. And that doesn't come immediately obvious just using this alone. So I'm going to use a gamma distribution instead. Then we can use moment generating functions to see what this distribution ends up being, because the moment generating function uniquely identifies the distribution. So a moment generating function of a gamma distribution, I'm going to actually call this W for simplicity. So a moment generating function W using properties of the gamma distribution ends up being 1t times beta minus alpha which in our case, alpha is equal to 1, beta is equal to 2, because this is a chi-square. So we have 1 times t times 2 minus 1. Now, how do we do this? So if we have a random variable and we want to find MW2, t is actually equal to MWT over 2, which ends up being 1 minus T2 over 2 minus 1. So we know that W over 2 ends up being a gamma distribution with shape parameter 1 and beta parameter 1. And that's it.